Welcome to reInvent. Thanks for coming to our session. This is MOB309. We're going to talk about developing serverless GraphQL architectures using AWS AppSync. I'm going to be joined by my two friends, Patrick from BMW and Nare, also from AWS. We're going to talk about some cool serverless technologies, talk a little bit about how BMW has been able to leverage GraphQL and AppSync and other AWS technologies to build the BMW personal assistant. And then we'll go through a couple new features as well. So here's a little bit of that agenda. Again, just GraphQL APIs. We're going to be talking about how we've used it at BMW. We'll talk a little bit about intro to GraphQL and an intro to AppSync to kind of give you a foundation. How to use AWS Lambda effectively with AppSync. So some patterns, some tips and tricks there. We'll then talk about building real-time applications on top of serverless architectures. And finally, talk about some new features in AppSync related to caching. So with that in mind, I'm going to welcome up Patrick, and he's going to kick us off. Please welcome.
Yeah, thank you, Mike, and welcome, you guys. I'm Patrick. I'm a software developer at BMW, and I would like to show you how we built a holistic data-centric GraphQL API for vehicle signals. But first, I would like to show you one reason why we need to transform the way we access data from the vehicles, the BMW's intelligent personal assistant.
BMW introduces your BMW Intelligent Personal Assistant, the soul of your BMW.
Hello, BMW. How do I activate the High Beam Assistant?
He is there when things don't go your way.
Hey BMW, I just want to relax.
If you like, you can give him a name. It will be his personal activation word.
Hey Joy.
Hello BMW, turn on executive mode please.
Whatever the situation, whatever your mood, you can simply feel at ease.
Hi BMW, activate expressive mode.
Or let the fun begin. This is your BMW Intelligent Personal Assistant, the revolution of driving pleasure, always by your side.
All right, so in order to deliver such unique and personalized driving experiences, we need to be capable of both processing large-scale real-time vehicle telemetry data and leveraging the data to derive insights and improve personalization for our customers continuously. And I would like to outline some requirements for this particular endeavor. First, we need to consolidate multiple data sources from the vehicle into a unified data model for machine learning and inference. So this acts as a kind of single source of truth. Second, we need to store the data historically for machine learning training and learn preferences. And third, there are also some use cases in this domain which require special query capabilities. So, for example, a machine learning model which tries to automate the seat heating function in the car wants to subscribe to a particular attribute like the exterior temperature or interior temperature. On the other hand, for example, a smart routing use case who wants to predict the destination of the customer during the journey, maybe is particularly interested in the vehicle's location and trace. So what are the challenges we typically face when collecting and processing telemetry data from our vehicles? So first, we collect the data from the vehicle through various channels related to certain use cases. So some of those channels collect the data in a redundant way, and often that's for a good reason. So for example, we collect the mileage at different points in the car to detect something like mileage manipulation. However, if you are an application who wants to consume this data, such redundant data collection introduces a lot of complexity. And those mixed data models are also often really use case centric, and some of them are well documented, but also some of them are not. And our idea was that we actually solve this problem with a kind of facade which acts as a central mediator between the car and the consuming services and hides away the complexity from the vehicle. And our data model is inspired by the vehicle signal specification, which has been published by the W3C community. And it basically allows us to map sensor data coming from the car to a coherent, harmonized data model, which can be exchanged between different use cases. So basically, we define two types of attributes. On the one hand, we have more stateless attributes like the vehicle's model or the fuel type, which come mainly from the vehicle master data. But on the other hand, we have also signal attributes which can change very frequently, such as the speed, the range, or the location. So having such a nice abstraction on top of the raw data, which you can query afterwards with GraphQL, gives you a really nice abstraction. And how does a query basically look like on top of GraphQL? So here, for example, we query the speeds of vehicles in a specific location. And in GraphQL, you can also define the response payload in the request payload. And in our case, we actually get 3 vehicles with a certain speed around this location here in Vienna. And you can use this information to trigger actions on top of that. So, for example, we could notify the cars about slow traffic. So having seen now the conceptual model behind the GraphQL API, let's dive a little bit deeper into our cloud-native architecture and how we process real-time data from the vehicles and make it available to consuming services. So on the left side, you can see that we actually ingest data from 2 different sources into our environment. So first, we have the data source, which is called Crowd Data Collector, and it collects a wide array of sensor attributes, especially for service improvement and personalization. And second, there is this latest state call, which is basically the last state of the vehicle, such as the current mileage or the current store status. And both data streams are directly pushed into Kinesis from the underlying source systems. And they then accordingly batched via firehose and persisted to S3, where we can use this data in a historized matter. It can be used by components such as SageMaker for machine learning models. We can use AWS Glue for ETL workloads, or we can query the data with SQL via Athena. And especially for machine learning workloads, we also save the model metadata in a dedicated model repository in DynamoDB. And this allows us to apply models on top of the real-time data stream, which resides in a so-called shadow zone. And this shadow zone is actually fueled by AWS Lambda, where we actually depersonalize by default and also identify which sessions belong to which vehicle. And we actually persist this data and transform it in the mentioned VSS format in a DynamoDB. And the data can be accessed via GraphQL and over AppSync. In addition to that, we also offer a subscription mechanism, so applications can register an SNS topic and subscribe to attribute changes based on a Dynamo stream. And this allows us to actually infer models if certain conditions hold true. And all in all, this end-to-end architecture allows applications to use models trained on the historized data and apply the models on the real-time data stream and trigger back actions to the fleet of vehicles. So now I would like to conclude with some lessons learned. So first, we have made really good experiences with GraphQL and its ability to define the response payload in the request directly. So this is quite contrary to a traditional REST interface where we always get the whole payload. And this enables us to query the data in a very flexible and efficient way and avoid unnecessary data transmission. Second, as mentioned, we initially started using DynamoDB for its scalable nature and built-in change stream. However, quite recently, we also investigated Elasticsearch. So especially its elegant query capabilities offer an interesting option for use cases with special query requirements, such as geo-range queries. And GraphQL's strongly typed interface gave us the freedom to change the underlying data source without affecting existing clients. So the last point would be that we also, on top of AppSync's subscription mechanism to GraphQL mutations, we also built our own subscription mechanism where applications can register SNS topics and subscribe to data changes in the DynamoDB table. However, we are also highly interested in AppSync's capability to use AWS Lambda to publish subscription events and subscribe to backend changes. And that's exactly what Mike is also showing you later in the session. And I would like to now take over to Nare, which will jump in and show you how you guys can build similar serverless GraphQL architectures using AWS AppSync. Thank you very much.
Thanks, Patrick. Hi, everyone. I'm Nare Haydapetan. I'm a senior software engineer with AWS, and I'm here to tell you more about GraphQL and AWS AppSync and how you can leverage AppSync to build services with GraphQL on top of AWS. So what is GraphQL? GraphQL is a query language for APIs. It includes a type system and a runtime for executing those queries. The type system lets you define a strongly typed interface. So what this means is you define your operations, which can be queries, mutations, and subscriptions, and then you define the objects that you're going to return from your service. The objects, in this example post, include the fields that are going to be returned, and the fields have types associated with them. Here, for example, strings, but you can also have integers, booleans, etc. And this lets you, ensures that your clients can only request the data that's available, and you can also provide helpful errors when they don't. There we go. Can change the slides. So the root types of GraphQL are queries, mutations, and subscriptions, as I mentioned. So with REST, for example, you have to make multiple API calls to request data from multiple data sources. Where GraphQL really shines is that it allows you to request data from different data sources in one call. So you can also filter this data on the server side, which means that when you request your data, that it combines all the data that you need, it filters out what you don't need, and this really saves, especially for mobile use cases, this is really useful because you only need to make one call. With mutations, you can update, delete your data from your data sources, and subscriptions allow you to subscribe to updates in your data sources. AppSync only allows subscriptions in response to mutations. So what that means is you can attach to any mutation, you can attach a subscription operation, and when a mutation happens, you will get an update, like a notification. So what's AWS AppSync? AppSync is a managed GraphQL service. It lets you connect to data sources inside and outside of AWS. It provides integrations with security services such as AWS IAM, API Key, Amazon Cognito, OIDC providers. It provides subscription support like we discussed, so you can get updates to your data. Caching, so you don't have to make a round trip to your data sources every time you make an API call. And it also provides integration with CloudWatch logs, so that makes debugging easier when something goes wrong. So coming back to the schema that you define, AppSync allows you to attach data sources to each field that you have. And you can also attach business logic to this, which we call resolvers. What that means, for example, is when you're executing a query, and there's a field that's being executed as part of that query, when you attach a resolver to it, that business logic will get run every time that field is executed. And you can attach these fields to different data sources, such as DynamoDB, Lambda, RDS, Elasticsearch, or any HTTP endpoint, which allows you to go outside of AWS to get data. Let's talk about the security integrations that I was mentioning. First is API Key. This is really useful when you're getting started or prototyping, but it's not as secure as the other options. When you would want to use API Key is, for example, when you just need to authenticate the users that are calling your service. So for example, when you want to throttle how many users can call your service, or you just want to know who's calling it, but you cannot really authorize their access. If you do want to provide more authorization features, you can use IAM, just like you do with any other AWS service. You can attach IAM access keys and users to your GraphQL APIs and provide authorization that way. Cognito user pools is another option that you have. This is useful when you have user pools and you want to group users and provide permissions that way. For example, you can have readers and writers and only allow writers to update your data. You can also use OIDC with any OIDC compliant provider. AppSync also allows you to do multi-auth. What this means is that you can attach different auth modes to different fields in your query. And when that query is executed and the field is run, that authentication and authorization credential will be requested at that point. You can do this yourself in your resolvers, in your business logic, but that field will get executed anyway, and with multi-auth support, if the credential is not valid, it will not get executed. An example of this would be if you have a public API, for example, you have a public web page that you want everyone to be able to access, but then you want something else, for example, an update page or a profile page, only to be accessed by certain users. So let's talk about some serverless use cases that you can use with AWS AppSync. Lambda is really useful in integration with AppSync. For example, as we talked about in resolvers, you can attach business logic to your resolvers. However, AppSync provides velocity templates for you to do this, which is really useful if you just have some simple logic that you want to integrate. However, it's not very powerful, and it doesn't allow you to use the language of your choice. So if that's what you want to do, Lambda really shines here. Another advantage is for you to be able to separate ownership. For example, if you have multiple teams that own different resolvers and different logic in your APIs, you can have these teams own and ship their own Lambda functions. And they can still be accessed by the same API and the same interface. Another advantage is if you want to access data in different VPCs that can live in different accounts even. AppSync allows you to access Lambda functions in different accounts, and Lambda has a lot of integrations with VPC that they've actually made a lot of progress on as well. Now VPC access is not as slow as it used to be. They've made a lot of progress there. So you can use that integration and all those features with AppSync now. So one best practice with Lambda, if all of your logic is owned by one team, what you can do is instead of attaching one Lambda function to each of your fields, you can implement all of the logic in one Lambda function. So all resolvers will basically just forward the data and the context and the arguments to your Lambda function. And then the responses and the errors will be forwarded out to your response mapping template and forwarded to the user. This gives you an example of the routing layer that you would have to implement in your Lambda function. And you would have these slides later so you can take a look at the code in more detail. But basically what this shows is that you get your types and fields names forwarded to your Lambda function. And here, based on that, you can forward this data to the resolver piece of code that you need implemented. And this is the business logic that you will actually implement for the resolvers. So once you actually forward all of your data to the resolver that you need, you have all the arguments and identity and everything that you would have just in your resolver function available to VTL in your Lambda function. And where this is really useful is that you can test this locally and just like you would with any other piece of code that you write. And it's maintainable, it's easier to test rather than having lots of templates spread out throughout your application. So now I'm going to pass it on to Michael to give you more context on Lambda and some other features that you can use with it.
All right, so I'm going to start out by talking about some features of working with AppSync and how you can do that. And one of the things that I'm asked the most through office hours and other conversations with customers is how do you take an AppSync API and expand it such that multiple teams can start to work with it, such that we can have one API that's not managed just by one team and that doesn't have to force all of those changes through the same pipeline. And there's a few things you can do to do that. So one of the things that makes it easy to do this and still effective and fits with our serverless use cases is that AppSync allows you to call functions in many accounts. We use the IAM-AssumeRole API in order to get temporary credentials such that we can make authenticated requests to resources in your own AWS account. And we can do that to do it cross-account as well. So you can have one AppSync API that delegates potentially to tens of functions distributed through different teams where each team can implement their own domain logic and have still this same cohesive API up front. From an operational standpoint, this allows teams in your organization to ship code independently. It also reduces blast radius, so if you make one bad deployment to one section of code, it will not impact the entire organization and the entire API. Using multiple functions in multiple accounts is also kind of a best practice from a perspective of reducing blast radius and improving security. So when I'm talking about reducing blast radius, there's a few things you can think of. One is just limits. So every AWS account has different limits. Putting a bunch of functions into one account can potentially, you can step on each other's toes in the limits of that function when it comes to concurrency or how many invocations you have, and you can split those concerns out into multiple accounts. And then the last piece is that you still, as the downstream function owner, contain and control all of your own access credentials, which enables us to do this cross-account call. So what you end up needing to do in this case is, as the function owner, you will create an IAM role with a trust policy to the AppSync service principal, and that AppSync service principal is then able to assume that role in all of your downstream accounts, such that the single API at the gate can talk to any number of downstream functions in any number of accounts. So this ends up looking something like this when you go down this pattern. So on the left, we've got this big query. We've got it's asking for both feed and profile information. The feed you can think of as, like in a social application, that feed is probably very personalized. It's generally attached to an identity. It's generally hard to compute. So it might take some background process to calculate some amount of relevance. Maybe there's a model involved that's placing posts into particular feeds. That can be its own team managed by, for example, a feed service. And then in the same request, we've got this top-level field asking for profile information for the currently logged-in user. That information might be stored in a JWT token. It might be stored in an identity provider like user pools, Cognito user pools, or in some external identity provider of your choice. And that's something that, again, could be totally separate, and not everyone might need to understand where that profile information comes from, but they do need to have access to it. So in this example, you can see we've got that big query coming in. That's going to come through AppSync in this top-level API team account. And then AppSync, as it's parsing that query and it's executing that GraphQL query, it's going to delegate the certain parts of the query's kind of functionality through resolvers into those downstream functions that can be launched in a VPC and access potentially siloed information in multiple downstream accounts and multiple downstream VPCs. So the whole point of this really is to create what I would call an organization-wide API. It's one of the things I think that is very attractive to organizations that are adopting GraphQL, is that it allows you to continue down the route of having many microservices managed by many teams, yet instead of having all of these different endpoints as you might in a traditional REST world where the client is going to do all this orchestration to route to a set of n endpoints depending on what service they're trying to talk to, it allows you to abstract that into one place via this GraphQL kind of routing layer that you can use to create that organization API. It'll create a well-defined type system that your front-end teams can use to understand what shapes are available, while still freeing up the back-end teams to make changes and replace implementations as they see fit. One of the really great parts about this is that it frees up from an operational sense those teams to operate independently. One way that this is used is you can generally do the data modeling process up front, decide on those shapes, what types do you need to expose, what access patterns does your application need, and you can do that really quickly and kind of write it up into a GraphQL schema using GraphQL SDL. Which is a schema definition language. And then once you define that shape, there's a lot of easy tools you can use to kind of mock that data on the back end, such that the front end teams can start programming against that unified data layer. Kind of like how Patrick was mentioning in BMW, they created that singular design, that singular data model for their vehicle signals. You can do a similar thing in your organization, and the front end can start working against that schema without waiting on the back end team to necessarily implement everything. The other part on the back end then is it gives you the freedom to implement it. You can mock it while you're doing the implementation, so you unblock the front end teams. And you can replace implementations as long as the shapes and access patterns remain the same. So it really frees up the front end and back end teams to get what they need without having to do an overabundance of coordination. Another piece of this that's not on the slide that is kind of more subtle in how this is impacted is just something that I've seen in practice is as teams generally start to optimize their API offerings and as they grow their features for particular products, they'll find that they end up starting to adopt more platforms. So this has an impact on how you consume APIs because a watch screen face might not need the same information that a desktop application needs. Where the watch might only need a title or some basic information to show kind of the minimal view, a desktop view might be giving you the depths of the information and going into details and showing you a bunch of information on what that particular view is. And to do that, you generally have a couple options. You're either going to end up writing like really rich REST APIs using query parameters and other sorts of kind of homegrown ways of saying, give me this but not that. Or you're going to end up building what I would kind of call like application endpoints. So it's something you'll see that you might have an endpoint that's specific to the watch, where the watch needs a stripped down piece of information, so the API is only going to give the watch a stripped down piece of information. On the desktop application, you might need the full payload, so then you might have a different endpoint that's optimized for the desktop use case. And in the end, what this is doing is creating more coordination between your front end and back end teams. Because every time the front end team wants to build a new feature or support a new platform or create a new view, they're going to have to go talk to the back end team and say, hey, you guys don't have an endpoint that quite does what we need. Can you create this or figure out a feature that allows us to do what we need such that we can strip down the resources that we're using and only get what we want? The part of GraphQL that fixes this is kind of just due to the nature of the language itself. Because in a GraphQL world, you define that data model up front, you define some access patterns that people find useful. You're able to associate objects of different types, so my posts can relate to my comments, and my comments can relate to authors. And then from the front end, you have the power to dictate what information do you actually need. And then you can write the query. That query is going to query your organizational graph. And then the view is going to be generated from the things that you need, but you're not actually dictated based off of what endpoints are available in the back end. So that's one that I think can really ease the process of building front-end and back-end applications. The other part of GraphQL that's really great in this organizational world is that it's not just the technology of GraphQL that you're getting, but you're also getting this rich community and this rich ecosystem of open source tools and open source clients and server software that you can use to get hires up to speed quickly. So the one that I generally bring up first is just GraphQL. So GraphQL is an open source IDE of sorts for GraphQL queries. It's kind of to a REST world what Postman is to REST, but that to GraphQL. And this, because GraphQL APIs are self-documenting, that means that their schemas are well-defined. You know exactly what types you're getting back, but you also have the opportunity to place documentation in those schemas that can explain what and why a certain thing is happening. And tools like GraphQL show this all in one view and give you things like autocomplete and kind of rich discoverability that you can use, and you can hand a new hire a link to a GraphQL instance, and within a few minutes, that new hire is going to be able to get caught up to speed really quickly in terms of what features and products does your organization provide via its API. It also does things like type checking and kind of completion, autocomplete, stuff like that makes it really easy that you don't even need to really know GraphQL to get started with a tool like GraphQL. So from a kind of onboarding perspective, it can do a lot of things. One other thing I want to bring up in that the link at the bottom of the page is that the last slide I was talking about how you can use you can launch Lambda APIs and VPCs to access potentially siloed data that traditionally would be hard to access, or you'd have to go build your own APIs and run new infrastructure to access it. But the Lambda team this year has done some really astounding work in terms of how they've improved their VPC networking. So there's a technology internally to AWS called Hyperplane that handles a bunch of cool things at a network layer, from multiplexing VPC access and other things that Lambda's been able to adopt, and has drastically improved the performance of Lambda functions that are launched in VPCs, which for us is great because all of our customers get the benefit from all the optimizations that the Lambda team does basically for free. So that's great, so I just wanted to mention that. So now to switch gears a little bit. So we talked about how to expand AppSync to do multiple teams and how to build that organizational graph. One of the things I want to talk about next is how to use AppSync to build real-time applications on top of serverless technologies. So one of the biggest value props of AppSync is that we do handle the kind of front-end WebSocket connection and distribution of messages in a kind of real-time world. So we will handle the fan-out, we'll handle the publishing, we handle the connectivity that customers are able to make connections that are subscribing to long-running processes. So we scale that whole front-end fleet for you such that you can still write things on Lambda that might not have persistent compute, but you're able to still benefit from all of this persistent compute capability that's being bundled into AppSync. Another thing about AppSync that Nare mentioned is that AppSync subscription events are triggered by AppSync mutations. So that's a design that was put in place to make it really easy for customers to subscribe to any mutable API change. This is really useful for traditional applications that are doing most of their interactions through their primary API. Say you've got a chat application where one application is subscribing to a chat room, and then another application or another person in the same application is writing messages. That mechanism makes it really easy for the customer that's subscribing to get notified whenever the other application creates a message, for example. But there's one kind of downside here is that a lot of times, and you can see this in the example that Patrick gave, where they're taking their vehicle specification information, running it through their models, making changes, cleaning it, putting it where it needs to belong, and then only after that long-running process do they actually want to trigger that subscription. So this is a use case that we hear a lot of as well, and it's actually not too hard to implement situations like this in AppSync. So now we're going to talk a little bit about how to do that. So with any AppSync subscription, there's a few things that you generally are going to have to do. At the top of this page, you're seeing this whole slide, I guess, is another example of GraphQL SDL. And you're going to see kind of our simple type system here, where at the type mutation is defining the root of our mutation operation in our API. It's going to define all of our mutable operations. It kind of maps to our posts, our puts, our deletes in HTTP. And we define this publish feed update field that takes this input of a post input object and returns a post. So these are kind of some stub things that are not shown, but the point is we want to have this publish feed update mutation that is basically there just to tell our AppSync fleet to deliver a message to a set of clients that have opened a subscription. The second type in here is the type subscription. There's kind of a lot going on here that I'll break down piece by piece. So at first you can see it's called onFeedUpdate. The feed ID argument in there is actually important. It's how you implement filtering of messages in AppSync subscriptions, and I'll get into that in a second. And then the last piece is that AWS subscribe directive. So that directive is kind of a utility that is put into the AppSync service that allows you to tell us what fields or what mutations should any particular subscription field subscribe to. In this case, we're saying that if I subscribe to the on-feed update subscription, I will be notified every time somebody publishes something through the publish feed update mutation. You can actually have multiple mutations in there, so you can have the same subscription or one subscription field be triggered by multiple mutations depending on how you want to implement that piece for yourself. So going back to this feed ID thing, I just want to focus on this because there's a little bit of subtlety happening here. So this feed ID is important because it's how you implement filtering in AppSync subscriptions. So as part of the way that we scale WebSockets, we don't want to ever over-deliver messages to people that should not be subscribing to those things. So the way that works is when I put this feed ID argument in here, when I publish a message, only messages that include the feed ID that are passed in this argument will actually be delivered. So if I'm trying to, as a user, I want to subscribe to my feed, I'll say subscribe to feed with feed ID, my user feed ID, whatever that is. And then when that comes through, our subscription resolver is going to have a chance to do connection time authorization logic. So I can actually run logic when somebody's trying to subscribe and say, hey, is this user actually the owner of this particular field or this particular feed? And if they are, I will allow the connection credentials and details to be pushed back to the client so that the user can subscribe. Then after that point, because I included the feed ID, say that the user successfully subscribed, every time a message is published, we're going to run that message through and say, hey, are there any active subscriptions where the feed ID is this specific value? That does the filtering that allows me to publish messages to a specific feed, but then know that a user that's subscribed to a different feed will not get pushed messages from another feed over here. So here's the next step of this whole process. So we just looked at the schema. This is the subscription resolver. So I just mentioned how you can use subscription resolvers to implement connection time authorization. This is kind of how it works. So on the left, you can see the subscription query that we would make. It's the same example. I want to get updates on a feed where the particular feed ID is coming in as a variable in the GraphQL query. That when AppSync fields that request, we're going to execute it, and we're going to dispatch your resolver that is attached to the on-feed update subscription field. In this case, you can see the resolver that I have on the right. It's pretty simple. It's for, this is an example of where VTL is actually great for simple gets and things like this. And what we're doing is I'm just running a get item against a DynamoDB table that presumably exists and that has a hash key that is equal to my feed ID. And as soon as I get that object back in the response mapping template, I'm going to be able to do my custom authorization logic. So in this instance, I'm just looking and saying, hey, does that table define an object where the owner sub is equal to the sub of the currently logged in identity? If it is, I'm going to allow that resolver to succeed, and then we're going to provide connection credentials to the downstream client so that they can actually subscribe to the event stream. And if you do not want them to be able to subscribe, and here's where you can run your implementation or your logic to say no, you can throw this error, and then the user's never going to get connection credentials, and they're never going to be able to subscribe to that feed. Here's the other side of that equation. So after we subscribe to a stream of events, we need to start propagating events through that stream. This publish feed update is an easy way to do so. You can see in this instance, our request mapping template is pretty minimal. We're just going to forward that input object we got through as the payload. And then that payload is a part of what I'd call a local resolver. When you're working with AppSync, you can see to choose a none data source. So basically say I don't want to have a data source on this resolver. And what that means is that all of this logic is actually just going to run locally, and we're not going to make any calls to any downstream services so that things stay snappy, and you can run basically your own logic without hitting any resources or having any extraditional cost to your account. In this instance, again, we're just passing it through as a payload. We're then going to return the result. And what that allows us to do is any system that we want to be able to publish can now send this pretty simple publish mutation. And then that's going to go through the AppSync filtering process such that it's only going to deliver posts where the relevant post ID or the relevant feed ID is present to whoever is subscribed using a query like we just showed on the previous slide. So why does this matter? This matters because it allows us to build more advanced use cases, kind of like Patrick described in their BMW example. We can run long-running asynchronous jobs, even batch jobs that are computing like complicated things. We can calculate relevance, run machine learning models, do all kinds of things in the background using Lambda and step functions and all those other great AWS technologies. And then as soon as we're done, we can persist whatever change we want into a DynamoDB table, for example. We can then stream changes into a Lambda function, and that Lambda function, all it has to do is send a simple request to AppSync saying, hey, I got this event. I want you to publish this event to whoever is subscribed to this. So you don't need any other logic to figure out who's subscribed, how to subscribe. There's no running WebSocket servers or anything. You just say, hey, publish, and then whatever clients are there that are connected and that have passed your authorization check are going to get delivered those messages after the filtering process happens, like we described before. All right, so that's serverless with real-time APIs. Now, to close up, I want to talk about a few new exciting features that just launched within the past month. And that is caching. So AppSync just released a native caching feature. This will work with any AppSync resolver and any AppSync data source, and it basically allows you mechanisms to define cache policies such that particular fields in your API will be saved and stored by AppSync, and then when subsequent requests come for those objects, we will automatically fetch them out of the cache instead of calling your downstream resources. There's no extra infrastructure involved in this, and AppSync will actually deploy this stuff on your behalf. So kind of a summary of what we just said. We'll automatically cache results. There's no extra infrastructure. This can help reduce compute costs, especially for slowly changing data. In the Lambda world, we're saving invocations. Even if you're using HTTP resolvers and running on things like EC2 or ECS, you can still reduce the amount of load that's going to be put on to specific compute options. From customers I've heard, this is often useful for things like catalog data or just things that change pretty infrequently. And then the last piece just says you can have different cache policies for different fields in your API because a post, say that feed, for example, that might be dependent upon who's logged in, whereas some other piece of information might need to be cached by like a post ID or some other change. So how does that look? It basically looks like this. So there's a simple new caching config option in all AppSync resolvers. You can define a TTL that's recorded in seconds. And you can also define a list of caching keys, which tell us basically how to identify a particular object that you want cached. So in this example, we're doing a top-level posts resolver. I've got this get post query. I'm resolving this post field. It's going to go to some post service or post data source, maybe on Lambda or even DynamoDB. And because I have this cache config, it's telling us, hey, I want you to preserve this feed for 10 minutes. And I want you to keep it identified or keep it unique to the currently logged in subject as provided by their identity, which is likely coming from a JWT token. So then every subsequent call from this user, maybe the user's just sitting on his phone, refreshing the page, looking for new posts. Every subsequent call is going to be fed directly from the cache. So then you can feel sure that you're only going to get one Lambda execution per 10-minute period for that particular field. The next block is talking about how we can provide a different cache policy to the author field. In this instance, it kind of makes sense because once I've made a post, that post author probably isn't going to change very often. In this instance, we have a resolver on the author field. Since that author's not going to change, I don't want to waste my precious executions on this thing that's never going to be changing and thus doesn't need to be recomputed. And also, this author doesn't depend on any subject. It's not dependent upon who's logged in. It's only dependent upon what post are we looking at right now. And that's what's going on here. So as I am able to cache this author field, I'm saying, I want you to cache this author for a full hour, and I want you to cache it based off the context.source.id. That source is, in GraphQL, referring to the parent object. So in this case, it is the instance of the post that is attached to this author. So what this means in effect is, hey, cache this author for an hour dependent on the post. So that any time that the author for this particular post is trying to be fetched, we're going to fill this request from our cache, and we're not going to hit that downstream Lambda and prevent that extra execution. So I show this with Lambda. But this, again, like I said, can be worked with any data source. So you can cache HTTP, Elasticsearch results, DynamoDB, RDS results, whatever you want. And there's no extra infrastructure from your perspective. You just kind of say, turn this thing on. You can tell us some simple things like how much storage do you need. There's a few tiers in there that give you options based off of how big your data is and how long you want it to be cached. So you've got a little bit of flexibility there. And that's already launched, and you can start using this today. So then to recap, so we are really excited about the things you can do with Lambda and AppSync. We're only going to keep building out these features. You can use Lambda to build powerful, testable resolvers. This is something that we've heard. I think VTL does some things really well, but in other instances, you really want to have your own programming language. You want to be able to write unit tests and do things like that. So this is a way to do so. It kind of keeps a clean request response model such that you can write integration tests and roll out code and write pipelines and do all the kinds of things you want to do to have a high level of operational excellence. You can use AppSync to turn your serverless app into a real-time one. We talked about that. We're going to handle the WebSockets for you. We'll handle the filtering and the publishing for you, the connectivity, and you can still write things in a serverless world without worrying about that. You can use AppSync and Lambda to subscribe to changes on the back end. So in our example, we showed subscribing to a DynamoDB stream, but you can do the same thing subscribing to an SNS topic or to a Kinesis stream or really any other real-time technology that you'd like to within AWS. The cross-account invocations make it easy for teams to work together. This, again, there's a lot you can do here. It's pretty flexible. You can have one account call into many accounts, and you still control all of the credentials and IAM access that you need. And then the last piece, which is exciting, is the new caching features that allow you to lower your compute costs with essentially no extra work. You just add these caching configs. You tell us how you want to identify objects. We will identify those objects, and then you will see fewer executions. So with that, we'll open up for questions. Thanks for joining, and if you have any questions, I'll field some now, and then we'll also be around after the session if you guys have any things you want to ask in a personal setting. Cool. Thanks, guys.